molecular dynamic simulations, grand canonical Monte Carlo simulations, vibrational normal modes, and phonons. So all features can be applied to external programs as well. The hybrid and multiplayer calculations can perform large variety of calculations for molecules as well as periodic systems with the hybrid engine. So any QM and force field based methods can be combined in any number of layers of mechanical embedding through a subtractive scheme. So electrostatic embedding through additive QMMM is available in a two-layer systems with ADF band or DFTB as a QM region. So then about Python scripting with PLAMs. For high throughput screening and workflows, we recommend Python library for automated molecular simulations, that is PLAMs, which is easily used with the entire atom Armstrong modeling suite. Then for parameter fitting for ReaxFF and DFTB. So the new PAR AMS or parametric AMS program lets you easily build training sets and parameterize ReaxFF and DFTB with the help of this interface GUI. And then Quantum Espresso graphical user interface, which supports the setting up running visualization results of open source periodic density functional theory, known as QE or Quantum Espresso. Then we have VASP graphical user interface, which simply support for the binary and VASP license. Then we have some other tools known as conformer module and also workflows to deposit molecules and average properties. So these are some of the areas of research which I will brief one by one. So in material science, it can predict and understand materials properties for atomistic simulations with periodic DFT for nanotubes, surfaces, and bulk. For example, in the bulk, we can use band quantum espresso ASE engines to reactive molecular dynamics with ReaxFF and machine learning potentials. So it can extract accurate material properties, including work functions, optical spectra, ionization potentials, band gaps, etc. So it can model physical processes based on large scale atomistic simulations for sputtering, aging, and chemical vapor decomposition. Then it can discover new materials with M3G NET. It's a new universal machine learning potential. Then comes the applications in batteries and photovoltaic cells, which we have discussed in the first days of the session. So it can accelerate the R&D, reduce cost, environmental impact, and safety to batteries and photovoltaics from fundamental molecular properties to large-scale reactive simulations of interfaces with explicit electrons. So how we can use this thing in AMS, that model reactions, diffusions, nucleations, such as lithium plating, and charge transport with ReaxFF and E-ReaxFF. Then we can use in the applications of polymers, how to build polymers to predict polymer cross-linking and degradation mechanism with ReaxFF. Tomorrow we are going to discuss about cross-linking polymerization. Then stress strain and failure mechanisms of polymers and composites to predict the glass transition temperature and thermal expansion coefficient. And also it will study the catalytic polymerization. And also in oil and gases, it can help to analyze the combustion reaction networks and kinetics. It will help to accelerate reaction dynamics into millisecond time scale. So in other words, it can help in analysis of bonding with activation string for rational catalyst design. And in nanotechnology, with the molecular as well as the periodic DFT codes, which we have discussed in the earlier sessions, ADF and band, it will help to study nanoparticles and molecular junctions with accurate treatment of relativity, fast TD-DFT methods, and specialized exchange correlation potentials. So it can predict the optical properties of quantum dots and other nanoparticles with ADF, and it can model relativistic nano-objects with our efficient and flexible embedding scheme via hybrid engine, which we have discussed in the last session, like QMMM, etc. It can also help to understand the nanoparticle formation and reactive process with the ReaxFF module. Then comes inorganic chemistry. In some of the applications in inorganic chemistry, which will help you to compute accurate spectroscopic properties from NMR chemical shift to X-ray spectra, which we are going to discuss today with one example. And also it will help to analyze the chemical bonding of various orbital decomposition schemes. It will help to visualize the energy level diagrams and orbitals. And also it will help to calculate excitation energies, oscillator strength, polarizabilities. And in life sciences, it can boost your research in pharma. It can help to study the ligand bonding conformations and absolute configurations with the DFT. The Cosmo RS module will help to quickly reduce the solvent mixture search of space for recrystallization. And it can predict the solubilities, log P, pK, DFT, and thermodynamics. It will help to optimize solvents, for example, liquid-liquid extraction for recrystallization. And also, AMS can be helpful for analyzing and predicting the NMR and VCD spectra. It will help to extract accurate energies for organic crystals. So these are some of the applications of AMS in various areas of research. So this, which I have already briefed. And this is about the ADF, which is a powerful software tool for modeling chemistry. And also this is about the graphical user interface. This is the representation of our ADF module, which can help to perform advanced simulations in a simple and intuitive approach. It will boost your productivity, whether you are a beginner or a seasoned computational chemist. The GUI is a cross-platform. It can run in Linux, Windows, and Mac OS platforms, and also provides interfaces of WASP and QE. So what can you build with the GUI? You can build molecules, periodic systems, polymers, and import structures from all major file formats. You can manage your jobs locally or remotely to a cluster computer. You can analyze the results of your simulations. You can extract the summaries of your calculations in structured data files or even CSV. You can visualize the structure, transition state, orbitals, densities, density of states, band structures, even spectra, energy, fitting results, etc. So this is about the overview about our AMS. This I have already mentioned about how and which always we can use AMS in various environments. And these are some of the material properties from SCM, which we can use for analyzing structural properties, thermomechanical properties, thermodynamic properties, and even some transport properties, and electronic, optical, and magnetic properties, which I have mentioned in the introduction. So these are about the material modelings and all. And this is about the benchmark studies about the hardware requirement. Net connection. Okay. So in general, the hardware will be the latest generation of processors, either 4 GB RAM per core or and an SSD. Based on the processor limit, you can set the uh, CPUs and all. So desktop or laptop, an Intel i7 processor from the latest generation can be recommended. So high-end workstation on a cluster. It's a dual CPU Xenon SP setup for at least 2 GB, but better 4 GB of RAM per core and SSD. Using an SSD becomes more essential as the number of cores per nodes increases. For calculations of multiple nodes, get a fast interconnect. So this is some of the representations of our benchmark studies and all. So let me go to today's presentation. Let me navigate to the software first. So this is the GUI which I'm going to start today's session. We are going to discuss about ADF, NMR, calculations using ADF. So I'm just giving a name. So I'm just giving input. Will take some time to run. First, so this is the interface. As I told earlier, we can upload any file formats in this interface, either a XYZ file or an SDF file. One second. Okay. So you can export and import this much file formats, small file, .stf, .cif, and even you can export it as some input files also. So this much options is indexed in this machine. Either you can load a PDB file or you can create many other file formats, I mean input files for other software formats. So I'm just copy pasting uh, XYZ file, which I have saved already. One second. Okay. Uh, so I just pasted that XYZ coordinates in this interface. So you can see that geometry. So now I'm going to do a simple optimization, geometry optimization for this structure. First, I need to set the task and let's see. So just setting that basis set to set P and then crossing. I'll brief you what are these methodologies for and then numerical quality effective and just so I'm just giving a name. So now I'm just going to run this geometry optimization. So you can see that the program is running. It will take some time. In the meantime, um, okay, 1 minute. So anyway, we are going to calculate the NMR spectrum here. So I have set the basis set, calculate some inputs. So the all electron basis set of TZP or higher can be a good choice for heavy metals when we consider for calculations related to NMR. PBEO is often a good functional for NMR because we can avoid, when we go for spectral calculations, we require some good functionals for relativistic approach. So we recommend this PBEO and spin orbit coupling should be used to provide for heavy atoms or light atoms. So the numerical accuracy should be better than default. So we can try the quality should either be good or very good to set the grid and density fitting accuracy. So these are the reason why we have set this numerical quality and frozen core. So frozen core in the sense means that to speed up the periodic or molecular DFT calculations, the inner electrons of atoms can be frozen, can be considered as a frozen. So not that this is not a pseudo potential. All electrons are still present in just frozen in the optimized atomic configurations. So the effect on the equilibrium geometry and the properties of valence electrons is usually small. So for this case, for understanding the spectroscopic properties of core electrons or electrons close to the nucleus, typically an all electron approach is necessary. So in the last session, I have told you that there is an atomic database which is indexed in this software. When you use the software, you can browse it from AMS Home or Atomic Data. So this AE basis set or atomic all electron basis set is denoted as element names, while the names are extended from the highest shell that is kept frozen for the frozen core. So for small cores, for example, I can show you none, small, large. So small cores in the sense means that, for example, if you take gold, which contains almost in gold 4D, so all 46 electrons up to 4D are frozen. Then the valence orbitals are 5s, 5p, 6s, 4f, 5d, 6p. So in the case of large core, we can consider the same gold 4f. So all 60 electrons up to 4 of our frozen cores, but the configuration will be krypton 4010 4 of 14. So the valence orbitals are in this case will be 5s, 5p, 5d, 6s, and 6p. Let me check what's the process going on here. Yeah, it's just running. So So in the case, what we have to focus is that we need to note that for some elements and some bases, there is just one core available. For example, one is for carbon atom, in which case all the core options default to the specific boson core. So when there are two other options available, the medium core option typically defaults to a larger core option. The use of medium core is therefore not recommended in these new versions. So we suggest to choose the specific basis set either from GUI, which we can see from this panel. This much options augmented J options are there available. And also by you can browse the available basis sets and specifically defining the appropriate core. So this is about the basic uh, information about these methodologies. Let's see what's the situation. What's the output? So it's sometime. I'll finish within some seconds. So in the meantime, any questions? Am I audible now? Any
Yes, sir.
breakage in my
I have a
sound?
question that
Yeah.
what type of progen core is to use which time? That is for a large system or for covalent system. That is there any rule that what type of progen core should I use?
So what type of metal are you using? For any example, can you say? See, I have
Suppose that
mentioned.
is zinc oxide cluster.
Okay, so that's what I specifically mentioned. For example, if that system is containing the configuration, for example, the valence orbitals. So you must focus on what are the valence orbitals and the configuration. I have pointed out two examples with gold. So in the case that you can either set a small core or as a large core, that depends on the configuration in this specific case. So there are two options.
Okay, and small core means that all electrons will be used in calculation.
Sorry, I didn't get the question. Can you repeat?
Small progen core, small means that greater number of electrons will be used in calculations.
See, for example, let me take an example of rhodium. So all 28 electrons can be used up to the 3D. But in the case of gold, small core will be 4D. So the 46 electrons can be. This is a typical example which I can say in the case of small core.
Okay, then which is recommended to use in calculations?
See, that's what I told you. That depends on the configuration. For example, in the case of rhodium, the configuration is argon 3D10. So, but in the case of gold 4D cases, it is krypton 4D10. So, depends on the configuration. You can use in the case of rhodium metal 3D10 up to 3D10 configuration you can use.
Okay, okay, sir.
In the case of small core. Okay, thank you.
Okay.
Okay, so the calculation is completed. 1 second. So now we will go for setting up the NMR calculations. So in this case, we will change this functional to GGA, P, BE, and the relativity is none. And then the basis set, we are just focusing to J, remaining as the same, and then I will so just running this calculation. Okay, so I have changed that basis set in J, including T set 2PJ, has been especially designed for ESR hyperfine splitting, and NMR spin coupling calculations. So it will take some time. It is running without any. So for when we are running the calculations for NMR, so an all-electron basis set of TZP or higher, TZ2P is usually the good choice, but for heavier metals, we will consider TZ2PJ or SORA, QZ4PJ basis sets. PBEO E0 is a good functional, but when it comes for higher end NMR calculations, we require a better basis set and basis functional. So the numerical accuracy, that's what I have mentioned in the previous experimental setup. I mean that in silico setup. So in this area of or in AMS suite or Amsterdam modeling suite, there is basis set. Which basis set? Basis set is one of the most important parameters. So we can some general recommendations as I have discussed earlier. So there is no definite basis set means, but you can check from literature and that how much fast and robust these basis sets are useful for our calculations. So the nomenclature of the STO basis sets in ADF, PT, and Q stands for double, triple, and quadruple. For example, you can see DZ, DZP, TZP. So, and NP stands for polarization functions. For example, there are some polarization function based basis sets in this database in the library. So the inner electrons of atomic fragments can be frozen during molecular calculations. So this is denoted with small, medium, or large, which I have told already, or by specifying up to which shell of electrons are frozen. So in general, we recommend the use of frozen core basis sets for LDA and GGA functions if available. So there are also specialized basis sets which contain diffuse functions, even tempered basis set ET for describing core electrons binding energy, and optimized for ESR, tensor and spin orbit coupling calculations for NMR. And also the DSP basis set could be a good straight point, especially for geometry optimization. In the first session, I have told you about geometry optimization, what are the necessary inputs which we have given to this case. And in general, this basis set is expected to be slightly better than that we used in 631 G star basis set codes in Gaussian basis set. So the DZP basis defaults to TZP for transition metals for more accurate predictions of spectroscopic properties. In the meantime, let me check what's the story. Okay, the calculations are moving a little bit fast. Okay. So usually an all electron basis set is necessary to properly describe the properties related to inner electrons. In the case of NMR, EPR, X-ray absorption. So and in the meantime, I have already told you one thing regarding the hardware. So we prefer an i7 processor for our latest generations. i7, i9 is preferable. And also for our high-end workstation or a cluster, a dual CPU Xenon SP setup with at least 2 GB, but 4 GB will be better. And so this is a case of our 2023 version. So after the session, anyway, I will share the slides and the recordings. Okay, let's see. So the atomic database can be available when you browse AMS Home or AMS Data. So in the interface itself, you can see once the calculation is completed. So there you can search the database in the search bar. So this is the interface where you can do the works and necessary analysis. The 3D interface. So 1 second. So speaking about the driver, so I told you in the previous session, this is our driver which covers this much modules. But in 2023, I'm using the 2022 version. In 2023, I think you come across some other modules also, new modules. So it is integrated with the ADF band, DFTB, MOPAC, molecular orbital package, ML potential, force fields, and reactive modules, reactive force field modules. It helps to explore the potential energy surface of your system of molecules as well as periodic systems. For example, through this much geometry optimization with or without constraints, advanced potential energy surface scan, transition state search, reaction barrier calculations, equilibrium and non-equilibrium molecular dynamic simulations, then vibrational normal modes and phonones. So in the hybrid and multi-layer calculations, researchers like us can perform large variety of multi-layer calculations of molecules as well as for periodic systems with the hybrid engine. In the last session, I have shown you about how we can do the QMMM methodologies, how we can set up those methods. So the Python scripting, we have the PLAMS, Python library for automated molecular simulations. That's the full form of PLAMS. Yes, the calculation is completed right now. And now we will check what we can go for the next. Okay. So now, so in the panel bar, you can see properties. So you can see bond orders, gradients, phonons, and elastic tensor, Raman spectral details, ESR, EPR. So here I'm going to select the properties NMR. Okay. So in this case, I want to click the checkbox of shielding for hydrogen atoms, and also the perturbing this one. The spin-spin coupling, that's our today's target, how to find it out. So the perturbing or responding on this, I'm just clicking that thing. And then, so after this, I'm just saving this file. Save. So it's an ethyl acetate, and I'm just giving it and score NMR, because we are going to calculate the NMR, theoretical NMR. So then we have given the name and then just running it out. Okay. So yes, this will take some minutes. So this AMS, our cutting edge software, is a state-of-art computational chemistry and material modeling software. It basically proves in the early days of computational chemistry, it has been grown to as a versatile chemistry and material modeling suite covering atomistic kinetics and fluid dynamics simulations. And for fluid thermodynamics, we have the Cosmo RS, Cosmo SAC, and Unified programs. I mean, for this thermodynamic calculations, and for kinetics, we have Kinetic Monte Carlo, microkinetics. And covering force fields, we have ReaxFF, ML potentials. For QMMM, we can use the hybrid engine. For type bending, we have TFTB module. For periodic DFT calculations, we have band and QE, quantum espresso interface. And for molecular DFT calculations, we have this ADF module for atomistic modeling. So the main applications, how we can extract accurate material properties or molecular properties, including work functions, the spectra, so the ionization potential, band gaps. In general, it can help to model physical processes based on the large-scale atomistic simulations of chemical vapor depositions related to band, I mean, this material modelings. So for periodic DFT calculations for nanotubes, surfaces, and bulk, we use basically band, quantum espresso, ASC engines, and for two reactive molecular dynamic simulations with ReaxFF and ML potentials. So then I have told already that we have sound applications in various fields in battery and photovoltaics, polymer modeling. So recently, I mean, how so we can use it for predicting glass transition temperatures, thermal expansion coefficients. It can design optimal solvent mixtures to dissolve the polymers using the Cosmo RS module. It can help to predict the important thermodynamic properties for polymers, for solvents, and polymer systems. So the CMS can be useful in nanotechnology as well as organic electronics. In organic chemistry, I have mentioned already life sciences. Now these days, in researchers in life sciences is getting more attention, especially in pharma. So it can boost our pharma research with AMS complete multi-skills tools. In the beginning, I told you it can focus on the study of ligand bonding, conformations, and absolute configurations with the DFT. So here also, in the case of pharma research, we can use Cosmo RS to quickly reduce the solvent mixture, especially to search space for recrystallization. And it can optimize for optimizing the solvents, for example, a liquid-liquid extraction. And it can perform large-scale simulations with the reactive force fields and machine learning potentials for biochemistry. So the search for conformers and refinements with the RD kit and crust. So these inputs are there in this backend. And we have the parameterization toolkit, which I have mentioned in the session about parametric AMS, which can create our own atomistic models to describe novel materials and molecules. So the parametric AMS can be easily developed with ReaxFF and DFTB parameters set with full support of GUI and the Python library for advanced customization. So once you go through the trial period, you can utilize all the modules. So what can we do in this parametric AMS is that we can import, build, and visualize training sets. And also, you can use data from AMS, WASP, and QE, various experiments into this interface. 1 second, let me check what's the story here. Okay, it's going on. I think it will finish within a few minutes. So coming back to this parametric AMS, so it can tune parameters to describe the properties such as energies, forces, geometry, band gaps, band structure, and you can use the validation set to prevent overfitting. You can submit multiple optimizations at the same time to explore the parameter space. And it can help to explore the sensitivity of the parameters to select to most meaningful subset to optimize. So speaking about the GUI, which we are seeing right now in your window, so it can build molecules, periodic systems, polymers, and import structures from all major file formats. I have shown you with this typical example that I have copy pasted XYZ file. So likewise, you can um, index multiple file formats because all are compatible in this software. So what all things we can do in the GUI, especially it's a good number of jobs where you can manage your jobs locally or remotely through a cluster computer. To a cluster computer, you can analyze the results of your simulation, MSD, mean square deviation, autocorrelation functions, histograms. You can extract the summaries of your calculations in structured data files that I can show you. See, you can export the same in different file formats, XYZ, and also so you can add the coordinates, you can export coordinates, and also you can visualize the structures, transition states, orbitals, densities, energy landscapes, fitting results. So more than hundreds of tutorials are available in our website and documentation also. So as I mentioned earlier, it is compatible in Linux, Windows, Mac, and also provides the interfaces of WASP and Quantum Expressor. It is one of the cross-linked, cross-platform GUI, which can be useful for beginners as well as experts. So this is about the GUI which I have mentioned. And so these are the properties. 1 second. In the meantime, that I can check that with the calculation. I can just the log file. Okay, calculations are running smoothly. So you can see that company constants and the running time. So it is taking 4 processes in a single node. Okay. So all these things are running in this GUI. So with the GUI, you can access all engines in AMS and perform advanced simulations in a simple and intuitive approach. So it will help to boost the project or the productivity whenever you are a novice or an intermediate or an advanced level user. So these are some of the applications of our software. Let's see what's the results. I think within 2 or 3 minutes, the results will be done. So So it will be helpful for predicting and understanding the spectral properties. So here in this case, ligand field DFT, which can deal with the near degeneracy of the open shell D and F elements with the good predictions for luminescence. For example, in the case of lanthanides or solid state lightning, and in the case of transition metal catalyst and actinides, and also for kinetics and reactivity, we can set up and visualize the microkinetics and kinetic MC simulations with the kinetic modules in the GUI, and also to get reaction rate and fluxes from reactive MD, we have chem tracers. For automatic PES exploration, I mean potential energy surface exploration and refinement, and visualizing the binding sites, we have the kinetics and reactivity interface. So within 2 minutes, I think we can wait 2 more minutes. Machine, the perturbation is going on. You can see that what are the calculations happening in this. So in oil and gas industry, as I told earlier that about chem tracer. So it can help to study the activation with the TFT, combustion reactions with the RNA and predict the vapor liquid equilibrium with the Cosmo RS in the case of oil and gas research. So how we can use this GUI, it can help to analyze the combustion reaction networks and kinetics, and it can accelerate reaction dynamics into a millisecond time scale, which is known as hyperdynamics, and also automate the potential energy surface exploration. And also it can analyze the bonding with activation strain model for rational catalyst design and optimize the solvents for extraction and other chemical processes. And it will take 1 more. Yes, it's almost done. So the screen catalyst for activity with the kinetic MC, and it can study complex combustion reactions. Almost tomorrow we are going to discuss about copolymerization, as I mentioned earlier. So there we will perform how to predict polymer cross-linking and also the degradation mechanisms with the reactive force field module or ReactSFF. So it will help to understand how we can model or how we can design a polymer in this same interface. So what will be our works which all happening here in this interface? So how to predict the important thermodynamic properties for polymer solvent and polymer systems. So in the first session, I mean first day one, we have discussed about batteries and photovoltaics. So how we can accelerate the research, how we can reduce the cost, the environmental impact, and safety of batteries and photovoltaics from fundamental molecular properties to large-scale reactive simulations of interfaces with explicit electrons. So it is almost convergence is going to function. Okay, did you try this AMS software? Any of our tutorials? Hello, am I audible? Okay. Yes. Okay. Thank you. I think this. Yes. Yes. Yeah. Okay. So the calculation that part has finished, and then we will go to the next step. 1 second. Okay. So now we will view the H1 NMR spectrum. So in this SCM, you can see there is one spectra in a single click. So now you can see the coupling 200 megahertz. Yes. So this is in the AMS spectra. This width, you can see the width. It's already 6.01. And you can see the atom is. We have given the file name as ethyl acetate 012 underscore NMR. The chemical shift ranges, and we see. You can see one by one that what are the chemical shift values. You can arrange it by just in the mouse. See. See, in the meantime, which hydrogen atom you can rotate by pressing the left. See, if I press the first hydrogen atom, it will show which hydrogen atom. See, this one is highlighted here. So H11, this one, and the value of the chemical shift. See, so I'm just clicking the plan. See. Now we can see that multiplicity. See the additional information regarding this specific hydrogen atom. See, so the spin-spin coupling within the emission frequency, it's a 200 megahertz spectrum which is displayed here in this interface. An additional section in the table will appear displayed. See, this is the information, additional splitting information regarding weakly coupled by atoms and splitting chemical shifts, strongly coupled by atoms, which all atoms are strongly coupled and which all atoms are weakly coupled with this specific hydrogen. Similar. Try. Second, just rotate. Okay. See, you can select one by one and you can analyze that which all um, protons are having that specific splitting. See the standard value as well as the scaling one by one. And also, so the average chemical shifts and couplings for equivalent atoms. So you have noticed that there are a lot of splittings in the simulated spectrum. This is because all the chemical shifts and coupling constants are calculated at a fixed geometry, which means that there is no rotation which would create magnetically equivalent groups. So you can resolve this issue either by flagging chemically equivalent atoms manually or have AMS spectra. So I can show you. I have already shown that thing. Just see. Once you're selecting that, just press the shift button and then control G. See. Once you select that, you can see that which all atoms. The same thing. You can select the region and you can check region wise how you can analyze those results. 1 second, I will show you by one. Okay. Just selecting. So you can see that that portion is selected. Likewise. So if you want to check one by one which all hydrogens, which all protons, which all chemical shift, you can just select it. Just press, just select by clicking shift. Select all these, highlight all these things, then control plus G. See. Now we'll go to NMR and then there's chemical equivalent regions. See. Now the spectrum it's displaying the region wise display. So this is about the overall NMR spectrum calculations using our ADF module. So any questions? So I have told you what are the initial setups which we have to create in the interface. And once this is it, first we need to optimize the geometry. Then we need to set the properties. So today I'm just summing up the case